Hello, this is Dr. Christy Patton-Lukes, and this is exam 3 for uh, Thermo 1, and this is our solution for that exam. If we look at question 4, it asks for what assumptions are required to turn the Clapeyron equation into the Clausius-Clapeyron equation. And so in this case, what we need to assume is that first of all, it's always that the vapor phase is an ideal gas, and that the volume of the liquid is much, much smaller than the volume of the gas, so therefore it can be ignored. We also have that one final thing where we say the heat of vaporization is more or less constant, and that allows us to do the integration. And so these three things are our assumptions for the Clausius-Clapeyron equation. In question 5, we're looking at a pump, okay? A pump requires work. Now, for the notation of this course, if we are bringing work into the system, that means it is positive. So N is positive. So the amount of work will be positive, so it means it's going to be either answer C or answer D. And then we also have something about the actual compared to the ideal. Now, the second law tells us that the reality is always going to be worse, right? And if I have to pay for this work to run my pump, I'm going to be paying more, so the actual amount of work will be more than this. We write this in terms of efficiencies for the process as the ideal work over the actual work to get a process efficiency that's between 0 and 1. But in this case, our answer is D. Question 6 gave you an opportunity to demonstrate what you know about all of that stuff with section 6.1, the math stuff. And so in part A, we're supposed to find an expression for dA in terms of T and P for a fluid, which says apply the fundamental relations to the expression this. And although we also had this on our formula sheet, I tried to make sure that it was here on this page simply to kind of give you a little of extra guidance on what you might do. So this is the fundamental relation. And so what I have is that, some people looked at this and said, well, maybe I should set these equal to each other. Yeah, but then I'm going to get something that maybe has a relationship to T, but not anything with V and P. And I only get two variables on any of these. The others are all interrelated. And so what I want to do to use the fundamental relation is just what we've been doing in class, where I say, well, let me take this differential form and turn it into a derivative. So for instance, dA dt at constant P is minus S, and I turn the differentials into derivatives. Okay, and in this case, dt at constant P, well, how does T change with T? It's 1. And so therefore I get minus S minus P dV dt at constant pressure. If I wanted to do dA dP at constant temperature, it is the same game. I'm going to turn the differential into a derivative. So I'm doing the same math operation on all of those differential pieces. So dt dP at constant T minus P dV dP at constant T. Now, dt dP at constant T, if T is constant, then dt is not changing, and so that's 0. So therefore, my answer to part A should be that dA is equal to minus S minus P dV dt at constant P, that's all times dt, plus negative P dV dP at constant temperature dP. Now, You're absolutely wrong. Several people put things where they had a differential was equal to a derivative. Go back and think about just the units. But mathematically, that's just not even possible that could ever be true. A differential is equal to a differential. It's not equal to a derivative. It can be converted to a derivative, but it is not equal to. Now for part B, what we are supposed to do is evaluate this for an ideal gas. And every time we get one of these expressions, remember I said that what you need to do is see whether or not this matches our expectation for an ideal gas. It's hard to verify the math, and so that's a way of doing it reliably. And so to do that, PV equals RT is our ideal gas law in terms of specific volume. And if I solve this for V is RT over P, then I can evaluate dV dt at constant pressure, right? Because if P is constant, R over P is the derivative. And dV dP at constant temperature, well, that's minus RT, those are my constants, over P squared. And so I can substitute those in. If instead of using the form that I gave, or that you derived, so let me just write that result down, minus S minus R dt minus RT over P dP. Some people chose to turn this into V. That's fine. It would be true also. Or you could use this version I started with here that just I gave you something. I just kind of randomly put letters together. In that case, T is equal to PV over R. And I need to calculate dt dV at constant P. And so that's just going to be P over R. And we've already figured out dV dP at constant temperature. And so for this one, the answer would be dA equals minus P squared over R dt plus TS, there's nothing that really can be done with that, plus P times negative RT over P squared, so minus RT over P dP. And if you look at this, this is clearly nonsense because the units are not consistent, but this was just an exercise in the math.